Welcome to the course Introduction to Mobile Robotics. Today we are going to see the last topic in this course, that is motion planning and control strategies. So far we have discussed path planning, which tells a robot where to go. Now we move to a more advanced concept, motion planning. Motion planning goes beyond just drawing a geometric line from start to goal. It considers whether the robot can physically execute the motion. For example, does the robot have a minimum turning radius? Are there limits on velocity or acceleration? Can it move sideways or is it non-harmonic, holonomic? A motion plan must avoid obstacles, respect dynamic constraints, respect dynamic limits, and produce smooth trajectories. So motion planning acts as a bridge between high-level power generation and low-level motor control. It ensures that what we plan is actually executable. This is a very important conceptual distinction. That is the difference between path planning and motion planning. Path planning answers where should the robot go. Motion planning answers how should the robot move. A path planner might generate a straight line, but if the robot is a car like it cannot move sideways. It must follow a curved trajectory. Motion planning converts the geometric path into a time parameterized trajectory. That means it assigns velocity, acceleration, orientation changes over time. So the output of motion planning is not just a curve, it is fully executable movement profile. This distinction is crucial for understanding real robotic systems. We'll see the types of motion planning approaches. Motion planning approaches can be categorized based on how deeply they model the robot's physics. Kinematic planning considers geometry and velocity constraints but ignores forces and inertia. Dynamic planning includes mass, acceleration, torque limits, actuator constraints. Advanced methods include sampling-based approaches like RRT, optimization-based trajectory generation. At this level, it is important to understand that motion planning ensures feasibility and smoothness, while path planning only ensures connectivity. Now that we have a planned trajectory, how does the robot follow it? This is where control strategies come in. Control systems continuously compare the desired motion and the actual motion. The difference between them is called tracking error. The controller generates motor commands to minimize this error. Without feedback control, even the best motion plan cannot be executed accurately. Control ensures stability, smooth motion, reduced oscillations, accurate tracking. So planning defines a goal and control ensures execution. Let us look at the three types of control strategies. Open loop control. Here, commands are sent without feedback correction. This is simple but unreliable. Any disturbances or modeling error leads to deviation. Closed loop of feedback control. Here, sensors such as encoders or IMUs provide feedback. The controller continuously adjusts motor input. PID controllers are commonly used for velocity and position control. This is the most common approach in mobile robots. Trajectory tracking control. This ensures robot follows a time-varying trajectory. Errors in position and orientation are computed, and corrective actions are generated. This is more advanced and used in autonomous vehicle and high-precision robots. The relationship between planning and control. Planning and control must work together. Motion planning generates a desired trajectory. Control ensures that the robot follows it accurately. If control is poor, the robot may drift. Overshoot curves oscillate, become unstable. If planning is poor, controller may struggle, motion may be jerky, physical constraints may be violated. So robust navigation requires both strong planning and strong control. Now the introduction to mobile robot system. Now we extend the discussion to mobile robot system. Instead of a single robot performing all tasks, multiple robots work together. Why do we use multiple robots? Because tasks can be parallelized, area coverage increases, systems become scalable. Failure of one robot does not stop the mission. This increases efficiency and robustness. Applications include warehouse automation, swarm robotics, environmental monitoring, search and rescue. Advantages of multi-robot system. Multi-robot system offers parallel task execution, that is, the task completed faster, increased coverage, large areas monitored efficiently, improved fault tolerance, redundancy improves reliability, scalability, system performance increase with more robots. However, coordination becomes more complex. Communication and collision avoidance between robots must be carefully managed. Coordination strategies. Coordination can be centralized or decentralized. In centralized system, one controller assigns the task to all robots. This simplifies coordination but creates a single point of failure. In decentralized system, each robot makes a decision independently. They communicate locally. Decentralized systems are more robust but require efficient communication and distributed algorithms. Modern swarm robotics often uses decentralized control. Next is the human-robot interaction. As robots move into human environments, interactions become critical. Human-robot interaction studies how humans and robots communicate safely and effectively. Interaction methods include speech, gestures, touch, visual signals. Three critical aspects of HRA are safety, robots must not harm humans; usability, interaction must be intuitive; trust, humans must feel comfortable working with robots; and communication, where a clear exchange of information is essential. Collaborative robots or cobots are designed specifically to work alongside humans safely. Challenges in HRA. Human behavior is unpredictable. Robots must interpret human intent, react in real time, avoid unsafe movements, maintain smooth and natural interaction. Advanced HRA integrates perception, decision making, and adaptive control. This is an interdisciplinary field combining robotics, psychology, and AI. In this module, we moved from simple geometric path planning to realistic motion planning and control. We then expanded into multi-robot coordination or human-robot interaction. This shows how mobile robotics evolves from pure navigation to intelligent and collaborative systems.